is working backwards. What's the assumption rule you're going to be using? So here it seems pretty straightforward that it's going to be arrow introduction. So for theorems are interesting in that, I mean, maybe not interesting because of this, but more straightforward because for the thinking backward strategy, you're just trying to figure out which assumption rule you're ending up with. So it really narrows it down to a choice of two, either negation introduction or arrow introduction. Okay, so arrow introduction seems like really the most promising strategy here. So in that case, the assumption is HB, and what we're trying to get is JB conditional HB conditional JB. All right. The next question you guys should be wondering is, can we get from this assumption to the consequent of the conditional that we're trying to get? And the answer is no, not yet. So we need to keep working backwards to introduce more assumptions. So arrow introduction is the likely candidate. For arrow introduction, we've got JB, assumption, HB, conditional JB. All right. Can we get there? No. So we need to make one last assumption. Arrow introduction again. So this assignment's more or less, I mean, this question's more or less teaching you guys how to nest assumptions and then satisfy the nesting requirements. So what we need is JB. This is like the mountain, the peak of our derivation, that once we complete this, we've completed everything we want. Okay, so we can get this just by reiterating, using that reiteration rule on line 2. All right. So I had some questions about that, so that's why I wanted to do that for you guys. Any other questions? Okay. So, all right, back to circuits. So let me switch this to the PowerPoint slide. All right, so on Wednesday, we introduced the idea of circuits and logic gates. So circuits are composed of logic gates and allow for operations similar to what our well-formed formulas do, where they take in a two-valued input and output a two-valued thing. Except in the case of circuits, those are bits instead of truth values. So you learned about 4 different logic gates, which have an equivalent table of operation to some connective from TFL. So there's the AND gate, which is analogous to the truth functioning of the conjunction connective, the NAND gate, which is not analogous to any single connective in TFL, but is analogous to the negated conjunction, or the Sheffer stroke. The NOT gate, which is analogous to the negation, and then the OR gate, which is analogous to the disjunct. And so what you're seeing here is a table of operations. So giving, specifying what the output bit value is for any two inputs. And then we talked about the idea of a circuit. So circuits are stringing together these gates into circuit boards. And what we're going to learn in this class is how to design circuits to perform certain functions. And so here's an example of what's known as a half adder, showing you how the input and outputs work for circuits. This is how, the signals in your calculator travel from the input to the output of your screen. Okay, so we sort of left off yesterday at making a pump circuit. I think we actually did this, but I want to review it quickly because this process is really important. So not making pump circuits, of course, but like so specifically, but just the idea of problem solving by taking a written description of some function and then turning it into a circuit design. And so this is really cool because it's what computer engineers do all the time. All right. So I'll show you guys how to think through this. So we've got a little bit of a description here. So very similar to what you do in solving those constraint problems we did earlier. You translate the description of the problem into parts that we can then use for putting together TFL well-formed formulas. Okay, so the first thing you do is specify letters that are going to stand for the inputs and outputs. So here we've got A is the input for pump 1, B is the input bit value for pump 2, and C is the output to the alarm, telling it whether it should signal or not. So you make a table of operations, which is exactly like a truth table, except it's composed of bits instead of truth values. And then we look at what the input-output operation should be. So the description here along the bottom, the output of the circuit should trigger the alarm in 2 cases, when both pumps are on and when neither pump is on, which means it should be a 1, the top case, when both A and B are 1, and then a 1 at the bottom case, when both of them are off. And 0 otherwise. Okay, so that's the first step when solving these problems, coming up with an input-output table that the circuit we're going to draw a diagram for is supposed to mimic the functioning for. Okay, the next step to help us along the way of designing a circuit. So once you get really good at thinking through these, you might be able to just jump into drawing up a bunch of logic gates strung together right away. But what's going to help us is to come up with a TFL well-formed formula that we can translate into logic gates. Because now we've got this scheme, right? We've got this idea of which gates have which operate in which way. So a really straightforward and uh, consistent method for doing this is going to be using a disjunctive normal form. So if you use disjunctive normal form because if you remember, what disjunctive normal form allows us to do is take a truth table or a table of operations and come up with a TFL general disjunction that has the same functioning. So with disjunctive normal form, we're paying attention to where the outputs come out as 1, and then making a general disjunction out of those. So that means creating a conjunct for each of those lines where it comes out as 1. And then gluing them together with a disjunction. So for this table of operations, it's just 2 lines that come out as 1. And yeah. Okay, here's what I want to do now. So this is the sort of the first half of solving these problems. And sometimes you might be given just a TFL Wolfram formula and asked to do the second half. So the next part is translating this well-formed formula into a circuit. And the way you want to approach this is the same way you would approach determining the truth value of the main connective given the truth value of the components. And to help you think through this, basically your circuit's trying to follow this path from the atomics to the output, which is the main connective. Not gate here, not gate here, and gate here. And so the truth functioning of this well-formed formula follows the blue lines in the same way that the bit functioning of the circuit's going to follow from the inputs to the output. Does that make sense to you guys? Yeah. All right. So the way you're going to draw up with the circuit is you're going to put as many inputs on, let's say, the left side as there are atomics in your well-formed formula. So not just unique, but the total number. And you're going to draw wires coming from each one going to the first gate that is analogous to the main connective next to those atomics. So for those top two, that would be the AND gate. Right? Because the AND gate is the one that functions closest to exactly like conjunction. So that's supposed to be AND. And then a wire goes from that to the OR gate. And then now we're doing the right side of that TFL Wolfram formula. Okay, I messed up. First, the A goes to a NOT gate. Oh, wow. It's so hard to draw. And B also goes to NOT gate. And then those two are connected to AND gate. these two are connected to, I sort of draw the wires wrong because it should be two wires going into the input, one wire going to the output. Okay. So, but the important thing here is this description or this process of translating from a TFL well-formed formula to a circuit and how it's mimicking the truth functioning of the well-formed formula and has this sort of same structure. So you're changing out the connectives for logic gates. Any questions about this process? No? Okay. So here's one way to do it. And just like with well-formed formulas, we can have, oh no, I lost. There we go. Okay. So just like with well-formed formulas, we can have more than one way to have the same functioning for a circuit. So we can draw up circuits multiple different ways. Here's an example of an alternative where it has the same functioning. So if we, no, I'm actually not gonna go through it, but yeah, I'll show you guys how to verify a circuit actually. So here's a circuit with the same functioning, just drawn a different way. So we want this circuit to function so that it comes out as 1, 1, 0, 0, 1, right? So it's 1 when both are on and 1 when neither are on, but not in the middle. So let's verify that. So we've got the starting value we're going to verify is 1. So 1 goes through the A wire and through the B wire into this AND gate, making this value a 1. And then we follow this other wire. 1 goes through this NOT gate, turning into 0. 1 goes through this NOT gate, turning into 0, which go into AND gate, turning into 0, which both those go through the OR gate, giving this value of 1 for that first input. So far we've verified that first input of the table of operations. Next, we're going to look at the second input where A is 1, sorry, and B is 0. So a 1 and a 0 go through the AND gate. 0 comes out through the NOT AND gate. A 1 goes through here, comes out as a 0. 0 goes through this NOT gate, comes out as a 1. Through the AND gate, comes out as a 0. 0 and 0 go through this OR gate, comes out as 0. All right, and so on. So that checks out. So just showing, I'm not going to go through the last two input outputs, but just showing you guys how to verify a circuit after it's been drawn up as a diagram. Okay. And here's an equivalent circuit, even though the gates are in a different order. In the same way that you can have, truth functionally equivalent well-formed formulas with different operators. Okay, so here's our next project. So what we're going to do together. So just a quick refresher on what we covered Wednesday with bits and binary and base 2. So a really common and one of the first features of computers and circuits was to perform calculations. And one of the first circuits used to do this were called adders. And in fact, you can go online and buy, let me see, can I get, yeah. You can go on Amazon right now and buy circuits that perform these basic functions. So 4-bit adder takes two 4-digit binary numbers and adds them together and gives you an output. These are $14 on Amazon. But that would be sort of complex for us to make at this point, or make a circuit diagram for, because we would have to have 8 inputs and at least 5 outputs, because you need the 4-digit binary number that's going to be the output, and then a carry digit to carry on to the if your addition adds an extra digit to the total. All right. So when it comes to binary numbers, each digit represents a 2 to the power of n number. So the binary number 110 is 6 in base 10. So here's 110 equals 6 in our usual way of counting. And the way you want to think of that is starting from the rightmost digit, you're counting how many 2's at an exponentially increasing number. So the first digit, in the same way, the first digit represents 1's in base 10. So for example, the number 326, the first digit is how many 1's are in the number, the second digit is how many 10's, and the third digit is how many 100's. But in base 2, it's the first digit is how many 1's still, the second digit is how many 2's, the third digit is how many 4's, the fourth digit is how many 8's, the fifth digit is how many 16ths, and so on. Okay, so here are some facts about adding binary numbers that are 2 digits. So what we're going to try and do here is create a circuit that's going to take as an input a 1-digit binary number, 2 1-digit binary numbers, and give us a 2-digit output. So an example, if this was like base 10, the operations we're looking at is something that would take x plus y and give us z, all right? Where x and y are just 1-digit numbers. So x is some number between 1 and 9. And same with y. And obviously, if you add 9 and 9 together, you would get a 2-digit number, right? So we have to have some way of representing numbers that go over the 1-digit count. Okay, but in binary, when you're adding 2 bits together, you're not going to be able to count as high as with base 10. So here are the 4 possibilities on the right-hand side. Right, so a 1-digit binary number, instead of being the numbers 0 to 9, sorry, 1 to 9, 0 to 9, yeah, I think you can call 0 a number. Instead of that, for bits, it's 0 or 1. So there's just 4 possibilities, right? In the same way that with a 2-value truth table, if we have 4 different 2 inputs, it's just going to be 4 possibilities. So here are the 4 possibilities. We either add 0 and 0 together, which gets us 0. We either add, or we add 0 and 1 together, which gives us 1, or we add 1 and 1 together, and that gets us binary 2. So the binary number for 2 is 1 and 0, right? So the first digit's the ones place, and the second digit's the twos place. Okay. So let's come up with a table of operations for these facts about binary addition. So this is how we're going to begin solving this problem. Okay, so our table of operations is going to look something like this. So we're going to call A and B the two inputs. So left side of, so A is going to be this input and B is going to be this input. And then S is going to be the first digit of the output, and then C is going to be the second digit of the output. So there's two outputs for this circuit, two inputs and two outputs. We'll organize the table of operations similar to how we've been doing our truth tables. So all possible sets of inputs. And then for the outputs, when it's 1 and 1, C, the carry digit, it's going to be 1, and the single digit is going to be 0. And then for all else, the carry digit 0. And then S is 1 for these two inputs and 0 for the other. Okay. So we're going to have to use, so in order to represent this truth functioning, if this was a truth table, we'd have to write up two well-formed formulas. And that's what we're going to have to do to translate this. So one well-formed formula to represent the output C, and then one well-formed formula to represent the output S. Let's start off with C, because that one's sort of easy. Can anyone tell me a TFL well-formed formula that has the truth functioning similar to C's input-output?
Conjunction.
Yeah. So just a conjunction. So that first circuit's going to be sort of easy to write. Second circuit, maybe not as easy. So we're going to use disjunctive normal form to form this second circuit. So it's the one where A is negated, and then you have B disjunct. And then okay. So now it's time to turn these into a circuit. Right. I'll let you guys do this on your own or try this on your own, and then I'll show you guys how it's done. So I'll give you guys a couple minutes to give this a shot on like a scrap piece of paper. And then, and then we'll finish up class by doing it together. So I'll be right back. Okay. So I'll just draw up the first part of this circuit. There we go. So we've got the A and B part. So we want to have an input A and an input B wire go into a gate, an AND gate, and come out and give the output for the carry digit, which is C. Next, we want to represent this well form formula. So we have 4 inputs for this one. There's 4 atomics. And then for this one, A first is going to a NOT gate, and then connecting to an AND gate. B is not connecting to a NOT gate. And then comes out, the wire comes out here and gets connected to an OR gate. And then the A on this side goes straight into the AND gate. So here with that, oops, this is the S output. So we've got a circuit here on the bottom that mimics the truth functioning of that well-formed formula representing the S column of the operation table. All right, so that's it for today. If you guys have any questions about the homework, email Thomas, not me. No, just joking. Or email either of us. Yeah, and yeah, we'll cover some more aspects of circuit building next week. So next week is going to be just focused on doing the computation side of things. So nice break from derivations. In fact, we won't be doing any more derivations until the final, which I think I've decided is going to be a take-home exam, or just like you guys have a week to do it, and then yeah. All right. I'll see you guys on Monday.